Hello, my name is Wim de Waele. I am professor at Ghent University in Belgium, and I want to present you our work on the evaluation of fatigue crack propagation in steel ESET specimens subjected to variable load spectra. So let me first set the scene. So we know that fatigue is omnipresent in mechanical engineering structures that are subjected to dynamic nature of load. In this work, we focus on offshore applications, for example, the monopiles that support offshore wind turbines. And due to the wind load and the wave load, as you see in the top right, they are subjected to load spectra that are characterized by variable amplitude. We know also that in steel specimens and in welds there might be some flaws present, which might impact structural integrity. So we want to know what is now the effect of variable load amplitude on fatigue crack growth. In literature, one will find different studies that focus on the effect of so-called overloads or underloads in an otherwise constant amplitude load spectrum on the evolution of crack length in a specimen. On the figure, you can see that the crack length is expressed as a function of applied cycles. The second line is for a constant amplitude spectrum, but all spectra which have an overload present lead to a slower pace in crack length increase or this crack growth retardation. At the extreme right, you see that an underload can lead to crack growth acceleration. So we will focus on variable amplitude spectra in this work. We will also focus on block loading schemes because we know that variable amplitude spectra are very difficult to perform in a laboratory setup, and we might be interested in how relevant is a block loading scheme for these variable amplitudes. Let me focus first on the experimental study. This slide shows the materials and methods that have been used. We selected an offshore steel grade and manufactured some standardized fracture toughness specimens. We selected the ESET configuration, eccentrically loaded single edge tension specimen, according to the ASTM standard. During fatigue loading, crack length was measured by unloading compliance. We have a clip gauge at the front of the specimen. It measures the crack mouth opening, and based on the compliance of the specimen, we can calculate the crack length. We also used direct current potential drop, but this is not further discussed in this presentation. And we also applied an optical technique, so we have some marker lines at the surface that allow us to follow the crack tip with a microscope, and that has also served as a benchmark for the DCPD and unloading compliance measurements. The first series of tests are the so-called block loading tests. So we have two different types of block loadings illustrated on the figures. At the left, going from a low stress intensity factor range to a high stress intensity factor range, and at the right, going from low to high and from high back to low. Further called in this presentation low-high sequence and low-high-low sequence. In the second series of tests, we focused on the random nature of load amplitudes. We did three different sets of tests. Let me focus on set 1 from the table. We started with defining a random load profile consisting of 400 values of stress intensity factor range. 400 values selected at random from 5 predefined different delta K1 values. This load profile was then further reduced by peak and valley analysis, which led to 236 values. Further reduced by also removing all the stress ranges below a certain threshold of delta K1, a threshold defined by experimental tests. And the peak and valley was also ordered by Rainflow counting, where you can see that we have ordered the stress ranges according to a decreasing delta K1 value. So the Rainflow has the same amount of discrete values as the peak and valley. All these load profiles have then been repeated a certain number of times to obtain the entire load spectrum. So for example, the set 1, there are 2000 repetitions of these load profiles that are being indicated. Set 2 and set 3 are similar. The main difference is that the load profiles are one order of magnitude larger in number of values, and accordingly the number of repetitions is then one order of magnitude lower to result in the same amount of total number of cycles. So let's look at some results, and first some results of the block loading tests. At the top right, you see the results of the low-high sequence. At the bottom right, you see the results of the low-high-low sequence. Focus first on the low-high, and let me, for example, illustrate what happens when we go from 9.81 to 14.4 47. The horizontal dashed lines indicate the expected fatigue crack growth rate expressed as dA over dN, calculated from an experimentally determined Paris law curve. But at the first transition, you see that the value of dA dN is much lower than expected and gradually start to increase again. So we have a significant amount of crack growth retardation. However, in next jumps, this is much less pronounced. The highest amount of crack growth retardation is, however, present in the high to low sequences at the bottom graph. So at the start, there is quite some noise. This is due to some bad experimental results. But if you, for example, have a look at what happens when you go from delta K equal to 32.17 to delta K equal to 22.52, then you see a very steep decrease in crack growth rate, and then gradually it picks up again to come at the expected crack growth rate value. So a very significant crack growth retardation. And the next transition, there is again a very significant drop. The straight line indicates that we lack some data in between, but you see a very significant decrease in crack growth rate, which starts to increase again, but it never reaches the expected value. And when we then dropped from 14.47 to 9.81, the crack stopped growing. So there was even crack arrest at these types of transitions. This slide shows the results of the fatigue tests using the random load profiles. If you look at the curves, they are of a quite continuous nature, so there are no distinct or very discrete events of crack growth retardation or crack arrest. What you can see is that the more repetitions we used, the larger the amount of fatigue crack growth rate. The more repetitions, the more random nature of the load spectrum, and probably load interaction effects cancel out each other. So load acceleration and load retardation compensate each other. The final fatigue crack lengths are thus decreasing with the decrease in number of repetitions, and very similar events have been observed for peak and valley profiles or reduced peak and valley profiles. Let's have a look at the Rainflow counted spectra. In these spectra, what you see on the graph in full line is the experimental value. In dashed line, there is the prediction based on calculations using the very conventional Paris law. Again, you see that the larger the number of repetitions, the higher the amount of fatigue crack growth will be. But you also see that there is quite a difference between the experimental values and the predictions based on the Paris law, which is not surprising. You should know that Paris law does not take into account any crack growth acceleration or crack growth retardation effect. So there are no interaction effects in the numerical curve. And of course, our experimental values will have these occurrences. Let me also stress the fact that the experimental curves are very smooth, but this comes due to some filtering. You will see on a later slide, slide 17, you will see that there is quite some noise, or at first sight it seems to be some noise on the curves, but I will explain that it is really effects of localized crack growth retardation effects. Again, the same effect of repetitions as on the previous slide, but here a very significant crack growth retardation can be observed. This slide summarizes all the experimental values of final fatigue crack length. What you can, for example, observe in the column set 1 with the largest number of repetitions is that the final fatigue crack length for random load profiles, peak and valley, reduced peak and valley, and Rainflow counted spectra are almost the same. They all range around the 10 millimeters. If we reduce the number of repetitions, if we go to more sequence effects, you see that there is a larger difference between the random load profiles and the other ones. Peak and valley and reduced peak and valley are very close to each other, but a very pronounced effect of crack growth retardation is present for the Rainflow counted spectra. You see that the crack length reduces significantly in comparison to the other load spectra. We also performed a small numerical study. We did a numerical evaluation for the Rainflow counted spectra because these showed most effect of crack growth retardation. We used an in-house developed Python-based framework that allows us to calculate crack length cycle by cycle. The framework allows to do this based on the conventional Paris law, which does not account for load interaction effect, or using some plastic zone models, the Wheeler and Willenborg models, that allow to evaluate crack growth retardation. Shortly expressed, if you apply an overload at the moment that the crack is here at the dotted line, you get a plastic field, a plastic zone by the light gray area. And when the crack starts to grow, for every subsequent load, you will have a certain plastic zone region again, the dark gray area. But as long as this zone is within the overload zone, crack growth is retarded. So here's some results. You see the experimental values in blue. You see the Paris law-based predictions in red, a very large overestimation of final crack length because it does not allow to take into account any crack growth retardation. In orange, the results from the Willenborg model, and in black, the results of the Wheeler model. You see that the Willenborg model is very well predicting the experimental values. Now this is not a filtered load signal again, and you perfectly can recognize the different profiles in the final signal. And if you look at the experimental values, you see a lot of crack growth retardation effects. You see that the crack length saturates at a certain value, then increases again. There are some strange drops. The delta A decreases. This seems as if the crack is shortening, but we believe that this is due to the crack closure effects due to the plastic zone at the crack tip. And now, coming to the conclusions. We have performed a study using ESET specimens that have been subjected to variable load spectra. First, some block loading tests have been done, and there we could observe some limited retardation effects in the transitions from low to high stress intensity factor ranges, but much more pronounced retardation and even crack arrest at high to low transitions. In the randomized load spectra, there was no significant sequence or interaction effects for load spectra based on a large number of repetitions of profiles. However, for the Rainflow counted spectrum or spectra, we saw a lot of crack growth retardation. We also performed some numerical simulations which showed very significant overestimation using the conventional Paris law and allowed good agreement while applying the generalized Willenborg model. Thank you for listening, and I'm awaiting your interesting questions. Thank you.